So as I said, today's topic is about rolling motion, how to describe uh, the rolling motion of an object, how to find out kinetic energy, angular momentum, how to write equations based on it. Fine. Now, you might have seen many objects which undergo rolling motion. Most common example is a wheel, wheel of a moving vehicle. Rolling is a case of combined translation and rotation, obviously. For example, if you consider the wheel of a vehicle, the wheel will be rotating around the axle and the axle will be moving forward. Okay, the wheel of a moving vehicle. Fine. So assume this wheel that you see on the screen is rolling in the forward direction. Okay. So it's a case of combined translation and rotation. Therefore, its center of mass will have a certain velocity in the forward direction. Let's call it as VC. And the wheel will be rotating also. Let's say its angular velocity is omega. I'm assuming it is rotating in the clockwise sense. Okay. And generally, if a vehicle is moving forward, the wheel rotates. Like if a vehicle is moving to the right, okay, the wheel rotates clockwise as seen by you. So let's say the angular velocity is omega and assume the radius of the wheel is r. Now you can see I have marked 3 points on the rim of the wheel. One point, the blue one, is in contact with the ground. At this moment, the blue point is in contact with the ground. Let's call it as P, the point of contact. Okay, there are 2 more points also. We'll discuss about them later. Okay. Now the wheel is moving forward with a velocity Vc and it is rotating with an angular velocity omega. It is rotating clockwise. Can one of you tell me how to express the velocity of any particle of a system which is in combined translation and rotation?
Sir, P is equal to velocity of PC plus velocity of C.
Correct. Velocity of P with respect to the center plus the velocity of center of mass itself. Good. Now velocity of center of mass is Vc in the forward direction. We'll take it as a vector. We'll just call it Vc I cap. Okay, Vc is the magnitude, I cap is the direction. Rightward direction, I'm calling it I cap. Okay. So velocity of center of mass is known to us. Next, we need velocity of point with respect to center of mass. Can any of you tell me how to calculate this? Velocity of the point with respect to the center of mass.
Sir, radius into omega.
Good, good. You have to consider the fact that relative to center of mass, all particles will be executing circular motion. So if you want to find out velocity of a particle with respect to center of mass, you have to make center of mass the reference. So with respect to COM, center of mass, the wheel will just be moving in a circle like this. Therefore, the point, the lowermost point that we have considered, okay, see, just for visibility, I have marked it as a thick point. It's actually one single point of contact between the wheel and the ground. Okay. In an ideal case, the wheel should touch the ground only at one point when you see from the side. In a real situation, there will be some flattening of the wheel. We'll discuss all that later. Okay. For now, we'll consider there's only one point of contact between the rolling object and the surface. Okay. When seen from this side. So with respect to center of mass, P should be moving to the left because the wheel is rotating clockwise. And with what speed will it be moving? V is equal to R omega. Now, R is the radius of the wheel itself because the point P is on the rim of the wheel. Okay. So VPC, the magnitude becomes R omega. Direction is to the left. So if you want to write it as a vector, it will be minus R omega I cap or R omega in the minus I cap direction. Therefore, velocity of P with respect to center is minus R omega I cap and velocity of center is VC I cap. Therefore, the effective velocity of the point of contact between the wheel and the ground becomes Vc minus R omega I cap. This is very important. Okay, you should actually be very comfortable writing expression for velocity of any particle of a system in combined translation and rotation. If you can do that, solving problems based on rolling will be very easy. Okay. Now, depending on the magnitudes of Vc and R omega, different types of rolling are possible. Let's consider the first case. Suppose Vc is greater than R omega. Okay, just to give you some context perspective, Vc being greater than R omega, let's understand what it means. Now, Vc, velocity of center of mass in the forward direction. No, due to that, all points will have a tendency to move in the forward direction. The entire wheel has a tendency to move in forward direction due to the velocity of its center of mass. Okay. Due to the rotation of the wheel, different points move in different ways. For example, if you imagine the wheel in pure rotation, the green point, which is the topmost point, will be moving to the right. The red point, which is at the horizontal level as the center of mass, same horizontal level as center of mass, will be moving downwards due to rotation. Okay. So due to rotation, different particles get different velocities. The point of contact gets velocity in the backward direction due to rotation. Okay. So basically what is happening with the point of contact is center of mass velocity is trying to take it forward. It is trying to take the point of contact also forward. But rotation is trying to make the point of contact go backward. Okay. So translation is trying to make it move in one way. Rotation is trying to make it move the other way. Now, which one dominates decides which way P actually moves. Okay. So suppose Vc is greater than R omega. Okay. Vc being greater than R omega means translation being much more than rotation. An example of this is when a fast moving vehicle suddenly applies brakes. Okay. If the vehicle is moving fast, obviously VC, velocity of center of mass, will be high. If you apply brakes, what will happen? The brakes will exert a torque on the wheel. Okay. And the wheel's rotation will stop. The wheel's rotation will get locked. As a result, the wheel will skid forward. Okay. And eventually it will stop. That's fine. But immediately when you apply hard brakes, what happens is the vehicle skids forward. Why? Because it has translation, but rotation is locked because of hard braking. Okay. So translation dominates, rotation is less in amount. As a result, what will happen? If Vc is greater than R omega, obviously the velocity of point P, like from this expression, from this equation itself, you can tell the velocity of point P, which is Vc minus R omega I cap, will be like if Vc is greater than R omega, this term becomes positive, no? So the velocity of point P, which is the point of contact, will be in forward direction. Fine. The wheel need not get completely locked also. Omega doesn't have to become zero, but if it becomes sufficiently low, if the rotation is too less compared to translation, point of contact skids forward. Okay. So this is a case of rolling with forward slip. Okay. So if V is greater than R omega, the object rolls with forward slipping. Slipping or skidding also you can say. Okay. Next. Suppose R omega is greater than Vc. What does R omega being greater than Vc mean? The wheel is spinning too much or too fast. Means rotation dominates translation this time. Okay. Now, when do you observe that? You can observe that if a vehicle is just starting from rest and it is suddenly accelerated at a very high rate. Okay. If you suddenly press on the accelerator, what will happen? Accelerator supplies fuel to the engine will rotate the wheel. So if you raise the accelerator suddenly, the wheel will have a tendency to rotate a lot, but the vehicle would not have attained forward velocity yet. Okay, enough forward velocity yet, because vehicle moving forward has to happen or happens due to friction from the road. Wheel rotation happens due to energy supplied by the engine. Fine. So if you raise the accelerator or if you press on the accelerator suddenly, what will happen? The wheel will rotate too fast, but the vehicle will take time to accelerate forward. So you will see the vehicle staying there itself, but the wheel spinning very fast. Or you will see the vehicle moving very slowly, wheel spinning very fast. Okay, some of you might have seen burnout videos. Okay, intentionally some riders, what they do is they apply the front brake so bike won't move, but they raise the accelerator, so rear wheel will be rotating, bike won't be moving. As a result, what will happen, due to the rotation of the wheel against the ground, friction will generate a lot of heat, the tire will get burnt. Okay, it's called burnout. So in that is an example of uh, too much rotation, not enough translation. So that is what happens when R omega is more than VC. And we know that the velocity of point of contact is VC minus R omega I cap. If R omega is greater than VC, what will happen? This term becomes negative. So the velocity
Sir,
of point,
so
ah,
is revving the bike a example of this?
see, revving is just rising. Like you can put the bike in neutral and rev it as much as you want. Revving is just like giving acceleration. I mean, not in physics terms. Revving is just like rotating the accelerator.
Oh, okay.
If you engage the gear, then you rev it, then burnout will happen. Okay. So yeah, in this case, the velocity of point of contact will be in the minus I cap direction. That means it will be in the backward direction compared to the motion of the wheel. Okay, that is also possible. Wheel is moving forward, but due to too much rotation, the point of contact is actually skidding backward. If it is done on a muddy road, the vehicle will even throw mud in the backward direction. Okay. So this is a case of rolling with backward slipping. Fine. Then the third case. Suppose rotation and translation are perfectly balanced. That means VC is exactly equal to R omega. Then what will happen? Translation is trying to make all particles move in the forward direction. Rotation gives velocities in different directions to different particles. The point of contact due to rotation has a tendency to move back. Translation is trying to take it forward. Rotation is trying to make it go back. If they are balanced, it will not move at all. Okay. This is what is interesting about rolling motion. The entire object will be moving, but the point of contact will not be moving. Except the point of contact, all other points will be moving. So if Vc is equal to R omega, the velocity of point of contact, which is Vc minus R omega I cap, becomes 0. Okay. This is what we call pure rolling. Or in questions, if they just say rolling, this is the case that you are supposed to assume. Pure rolling. Rotation and translation are balanced. So in this case, there won't be skidding. And this is what happens usually when you drive a vehicle without skidding. Okay. Whether you are riding a bicycle or bike or car, whatever it is, if the tires are not skidding, it means the car is in pure rolling or the tire is in pure rolling. Okay. So the wheel will be rotating as well as translating, but the point of contact will be at rest. Okay. And if one particle of a system is at rest, okay, if one particle of a rigid body is at rest, then we can tell for sure that the entire system must be in pure rotation about that point or about that axis. So this also becomes the instantaneous axis of rotation in case of pure rolling. Now, how am I concluding this? Like last class we discussed how to identify instantaneous axis of rotation. Now you consider this rod example itself. Most of you could even tell on your own where the instantaneous axis of rotation will be. We looked at the velocity profile. Okay, one particle's velocity was 7 meters per second, one particle was 5, one particle was 3, then 1, then 0. Whichever particle's velocity is 0, okay, whether it's a real particle of that system, actual particle of that system, or it's an imaginary particle when we extend the system, that particle lies on the instantaneous axis of rotation. Okay, so same thing in case of a wheel also. Any object which is undergoing combined translation and rotation, if you can identify a point which is at rest, at that moment, that itself will be the instantaneous axis of rotation. We'll prove this also mathematically. Fine. So what is the condition for pure rolling? The condition for pure rolling is that velocity of center of mass should be equal to r omega. See, sometimes even if Vc is equal to r omega, the system won't be in pure rolling. How is that possible? Because there is a proper direction in which it is supposed to rotate. For example, if Vc is in the forward direction, as you see here, omega has to be clockwise. Only then translation will give the point of contact forward velocity, rotation will give you the point of contact backward velocity, and they'll balance. They'll cancel out. Suppose Vc is equal to r omega, but omega is in the anti-clockwise sense. If omega is like this, then due to translation, the point of contact has a tendency to move forward. Due to rotation also, the point of contact has a tendency to move forward only. Then how can it be at rest? It will skid. Okay. So don't blindly remember the condition for rolling as V is equal to r omega. The sense of rotation should be appropriate. Okay, that is also there. So you need to check whether it is rotating in the proper appropriate sense or not, clockwise, anti-clockwise. Fine. We'll solve some problems based on this. First one. Let's say there is a disk of mass 4 kg, radius say 20 centimeters. It is rolling on a surface with a speed of 10 meters per second. Okay. Rolling is a case of combined translation and rotation. I have given you the speed of the object. First, calculate the kinetic energy of translation. Calculate kinetic energy of rotation. Total kinetic energy. Solve this, all of you. Okay. The formula for translational kinetic energy is half m VCM square. So half mass of the disk is 4 kg, VCM is 10. Square it becomes 200 joules. Like Rishi, why did you not give an answer? Where
Sir,
are Rishi? Huh.
moment of inertia of disk.
Okay. The moment of inertia formulas you will have to remember. No other choice. And keep solving problems. No, it will automatically get registered in your brain. Okay. Rotation, kinetic energy of rotation is half ICM omega square. When a disk rolls on a surface, okay, the axis of, you have to take an axis passing through the center of mass in the horizontal direction, perpendicular to the plane of motion of the disk. So it will be the own axis of the disk. And moment of inertia of a disk about its own axis is mr square by 2. Mass of the disk is 4 kg. Radius is 20 centimeters, that is 0.2 meters. Square it. Mr square divided by 2. That is half ICM multiplied with omega square. How much is omega in this case? See, you are given that, you are told that the disk is rolling. So in cases of rolling, they will only give you one of the two terms. They'll either give you V or omega. They won't give you both. Okay. And you know that in case of pure rolling, V is equal to R omega. I told you, no, if it is just given rolling, you have to assume it is pure rolling. So omega becomes V by R. And you have to square that because you need omega square. V is 10, R is 0.2. Square it, you get 10 square divided by 0.2 squared. So this is half ICM omega square. 0.2 square will get cancelled. 4 and 2 will get cancelled. 10 square is 100 joules. That's all. Total kinetic energy then becomes 300 joules. So remember, in cases of rolling, they'll give you only one of the two terms, either velocity or omega. You can find out one based on the other. Is it clear? Any doubts in this? Okay. Next, let's use this picture. Fine. Assume this is an object of radius r. Center of mass is moving with a speed vc. And angular velocity is omega. It's in pure rolling. Okay, wait. Fine. It's in pure rolling. Derive velocities of the topmost point. Topmost point, let's call it A. And the point which is at the same horizontal level as the center of mass, let's call it B. Derive velocities of points A and B. And answer should be in terms of VC. Try. I'll give you all 2 minutes. Any answer? Okay. So suppose you want to find out velocity of A. General formula, velocity of A with respect to center of mass plus the velocity of center of mass itself. Now we know the velocity of center of mass, VCI cap. Now we need velocity of A with respect to the center of mass. So you have to imagine the system undergoing pure rotation about the center of mass. We have already done that also, like this. So if the system is in pure rotation about the center of mass, the topmost point, that is A, will have a speed of r omega because its distance from the center is r, okay? Because the distance from center is r, it will be r multiplied, like same as the radius, it will be r into omega. And the wheel is rotating clockwise, right? Therefore, that point, the topmost point, will be having a velocity in the forward direction. So its velocity is r omega I cap with respect to center of mass. Rishi, is this clear?
Yes, sir.
Why? Where were you stuck? Why were you not able to answer this problem?
Sir, I was not able to get that part of it.
Okay. So effectively, it becomes VC plus r omega I cap. Aishwarya, is it clear?
Yes, sir.
Now, you are told that the system is in pure rolling. In pure rolling, VC is anyway equal to r omega. So if VC and r omega are equal, then this becomes 2VC I cap. Okay, so the topmost point will actually be moving twice as fast as the center of mass. Exactly twice as fast as the center of mass. Fine. Next, the point B. We need the velocity of B with respect to center. Okay, velocity of center is already known. VC I cap. Because the wheel is spinning clockwise, B with respect to center of mass will be moving in the downward direction. And B is also a point on the rim of the wheel itself. Therefore, it is at a distance equal to radius from the center. Okay, so that will also be r omega. The speed will be r omega again. but the direction is downward, so minus j cap. That is the velocity of B with respect to the center of mass. Minus r omega j cap. So effectively it becomes Vc I cap minus r omega j cap. Now r omega is same as Vc because the disk is or the object is in pure rolling. So Vc I cap minus Vc j cap. If you want its magnitude, it will be root 2 times Vc. Okay, root of x component squared plus y component squared, you will get it like this. Okay. Now, let us imagine how they actually move. A's velocity is 2 times Vc. Okay. Let's say the center of mass is moving with some velocity in the forward direction. Let's indicate it with a vector like this. Okay, the yellow vector indicates velocity of center of mass. Then A's velocity being twice as much as that of the center of mass will be like this. Center of mass velocity being Vc. Okay. Now, this way also you can tell that the lowermost point, the point of contact between the object and the surface, is the instantaneous axis of rotation. Okay, this is the idea that we used in the last class to find out instantaneous axis of rotation. We draw perpendiculars to the velocities of two particles. Now, if you draw perpendiculars to the velocities of the topmost point and the center of mass, those two perpendiculars will be the same line, this line. So the instantaneous axis should be somewhere on this line. And then you look at the velocity profile. As you go down, the velocities will decrease, and exactly at the point of contact, the velocity will be 0 in case of pure rolling. So the point of contact, the axis through the point of contact becomes the instantaneous axis of rotation. Okay. Now observe velocity of the particle B. Velocity of B is Vc I cap minus Vc j cap. Vc I cap will be this way, minus Vc j cap will be this way. Okay. Both components equal. So the exact velocity of the point B will be in this direction. And its magnitude is root 2 times of Vc. Okay. And see, this vector, the actual velocity of the particle B, has equal x component and y component, means it will be making 45 degrees with the x-axis and also the y-axis. This angle is 45. Now you draw a line connecting the point of contact and the point B. Okay, you imagine a line connecting the point of contact and the point B. Since point B is at the same horizontal level as the center of mass, geometrically we can say that this angle will also be 45 degrees. Now, if this is 45 degrees and VB makes 45 degrees below x-axis, then this angle becomes 90 degrees. Fine. This is another way in which we can say that P is the, or axis through P is the instantaneous axis of rotation. Now we know VB's velocity. You draw a line perpendicular to VB's velocity. Okay. You draw a line perpendicular to A's velocity. You draw a line perpendicular to B's velocity. They both meet at the point of contact. Therefore, that becomes the instantaneous axis of rotation. Okay. And you can use this in reverse also. Now that you know the instantaneous axis of rotation, you can tell velocities of particles directly. Okay. Now the rolling wheel is a system in combined translation and rotation, but you can think of it as being in pure rotation about that point of contact. Okay. That is how it is useful. Let us make use of that in this problem itself. You are asked to find out velocities of A and B. Okay. Now you tried using VA is equal to VAC plus VC and VB is equal to VBC plus VC. That's fine. Nothing wrong with that method. But we know that this is the instantaneous axis of rotation. Okay. It's a very powerful idea, actually, very useful idea. about this axis, all particles will be in pure rotation and they'll all be rotating with the same angular velocity omega. Okay. From the point of contact, how far is A? 2 times the radius. Therefore, you can directly tell, okay, just draw a line from the instantaneous axis of rotation to the particle P. Okay, the length is 2r. So you can directly tell that A will be moving, like A is in pure rotation, no? In pure rotation, how do you write velocity? V is equal to r omega. But from axis of rotation, you will have to take. Okay. From axis of rotation, the distance is 2r. So you can directly tell that the velocity of A is 2r omega. Next, B. You have to imagine B in pure rotation about the instantaneous axis of rotation. So draw a line connecting them first. And B's velocity should be perpendicular to that line. So B's velocity will be like this. And how much will it be? Again, distance multiplied with omega. Now, from the point of contact to center of mass, the distance is the radius. From center of mass to the particle B also, the distance is the radius itself. So radius perpendicular. This distance becomes r root 2. Therefore, B's velocity becomes r root 2 times omega. Or you can say root 2 times of r omega. That is root 2 times of Vc. So you can make use of the instantaneous axis of rotation to tell velocities of particles without always applying that Va is equal to Vac plus Vc, that formula. Is this clear to both of you, Rishi, Aishwarya?
Yes, sir.
Okay, let's see if you can solve this. This involves a little bit of mathematics. Again, the object is in pure rolling. And this time you have to find out the speed. Okay, just the magnitude of velocity of which particle. Okay, let's mark a particle here. Call it X. And where is X? The line connecting point of contact and X makes an angle 60 degrees with the surface. Okay. What all are you given? Vc is given, obviously. And you are told that it is rolling. Okay. Then you know that there must be an angular velocity. You can tell how much is the angular velocity also. V is equal to r omega. Omega is V by r. Radius is r. Derive the speed of the point X. Think carefully. As I said, little bit of mathematics. Some ideas from geometry are involved in this. Okay, I haven't gotten any answers, but how are you trying to solve, Rishi? Like, what's your idea? No response. Aishwarya?
Sir, I initially wrote velocity of Vx plus Vcm is equal to velocity of x.
Okay, you wanted to try it that way. Vx is equal to velocity of x with respect to center of mass plus the velocity of center of mass. Okay, then where did you get stuck?
Finding velocity of Vxc.
Velocity of x with respect to center of mass. The direction might have been a problem, I can guess. Magnitude is not an issue. It is again r omega only. Exact direction you need because these are vector quantities. Okay, fine. So that's where I said some geometry will be applicable. You can use another idea also that the point of contact, I'm telling this to both of you, the point of contact is the instantaneous axis of rotation. Okay. Or the axis through the point of contact is the instantaneous axis of rotation. So if you can somehow find out this distance, let's call this as L, then you can directly say that this particle X will be moving with a velocity or with a speed L omega in this direction. But we need that distance. That distance is not 2 times the radius. Okay. So consider a circle. From the side, the rolling object looks like a circle. And you need the distance between this point, the bottommost point of the circle, and some point here, which makes an angle 60 degrees with the horizontal. So it will be making 30 degrees with the vertical. The line connecting them will be making 30 degrees with the vertical. Fine. This distance is 2 times the radius. This angle is 30 degrees. Now you must have studied in mathematics that the angle in a semicircle, or the angle subtended by the diameter in the semicircle, is always 90 degrees. These two will be perpendicular to each other. You take any point on the semicircle and connect that point to the ends of the diameter. This will definitely be a right angle. Okay, it is one of the properties of circles. That's all. Then you have a right angle triangle. In a right angle triangle, if you know the angle and one side, you can find out any other angle and any other side. So for 30 degrees, L is the adjacent side, 2R is the hypotenuse. That's all. So cos 30, or you can say L is equal to 2R cos 30. Cos 30 root 3 by 2, root 3 cancels. That distance is R root 3. And if that distance is R root 3, then that particle X will have a speed of L omega, that is R root 3 into omega. Done. You can solve it the other way also. You can find out the velocity of X with respect to center and then use that this formula. Now, if you want to find out velocity of X with respect to center of mass, you need to know, we need velocity, means we need the angle at which it is moving. So connect the center of mass to that particle first. X with respect to center of mass will be moving in this direction. It will be executing circular motion around the center of mass. So Vx, see, the distance is r itself and angular velocity is omega. So the magnitude of velocity of X with respect to center is r omega itself. What we want is the direction, the angle at which it is acting. Now, if you know this angle, theta, then you imagine drawing a horizontal here. If that angle is theta, this is 90 minus theta. Vxc will again be making theta with the horizontal or with the x-axis. So what we need to find out is that angle theta. Can any of you tell me from properties of circles how much that angle will be?
So 60 degree.
60 degrees. Okay, it will be double of the angle it subtends on the circle. Okay. I don't, what exact property is this? Like, what is the statement for this property? Okay, fine. You find out. Okay, it is there in properties of circles. That angle will be 60 degrees. Now, if that angle is 60, Vxc will also be making 60 degrees with the x-axis. Therefore, we can now write it as a vector. Velocity of x with respect to center of mass is r omega into magnitude is r omega cos 60, that is 1 by 2 I cap plus sine 60 root 3 by 2 j cap. Okay. Therefore, the effective velocity of x Vxc plus Vc, that is, okay, r omega is nothing but V. So V by 2 I cap plus V root 3 by 2 j cap, that is velocity of x with respect to center of mass, plus the velocity of center of mass is V I cap. I'm not writing Vc, I'm just writing V. Then V plus V by 2 becomes 3V by 2 I cap plus V root 3 by 2 j cap. Now V root 3 by 2 can be taken common. You will be left with root 3 I cap plus j cap. And the magnitude of root 3 I cap plus j cap is under root 3 square plus 1 square, that becomes 2. 2 cancels. You get the answer as V root 3. The magnitude as V root 3. And that is what we got by using instantaneous axis of rotation also. We got root 3 r omega. That is nothing but v root 3. Okay. And see, not just velocities, you can even find out accelerations of particles in pure rolling using a similar idea. Suppose you want acceleration of point. Okay, acceleration is a. Suppose you want acceleration of the point of contact. Then you write it as acceleration of point with respect to center of mass plus the acceleration of center of mass. Okay, derive this, both of you. I'll copy paste the diagram. I'm asking you to derive acceleration of point of contact only. And okay, I have to give you what is the acceleration of center of mass. Assume center of mass is not accelerating at all. Let's say acceleration of center of mass is 0. What is the acceleration of point of contact with respect to center of mass? I mean, how much? What all are you given? You are given r, you are given omega. Or you may be given v also. If you are given v, indirectly you are given r. Okay, based on this, you try to derive. Any idea how to express acceleration of the point of contact with respect to center of mass? You just have to imagine the wheel rotating. Translation doesn't have to be considered. If the wheel
Sir,
is
is it
rotating,
v squared by r?
correct, correct. The wheel is rotating means every point will be executing circular motion, okay, about an axis passing through the center of mass. And in circular motion, there will definitely be radial acceleration, okay, or centripetal acceleration. There may also be a tangential acceleration, but radial will definitely be there. Radial means acceleration directed towards the center of the circle. Okay, so the point of contact will have an acceleration in the upward direction relative to the center of mass. Okay, or with respect to center of mass. It may even have a tangential acceleration if alpha is there. Okay, that is not given to you in this question. I must have given actually. Acceleration of center of mass is 0. Assume alpha is also 0. I'll also tell you what will happen if alpha is non-zero. But due to omega, I mean due to rotation, centripetal acceleration will be there. Okay, I should not say due to rotation. Any object in circular motion will have centripetal acceleration. Okay. What is the formula for centripetal acceleration? V square by r. You can also write it as r omega square. In which direction will it be? Towards the center, means j cap. Therefore, acceleration of the point P with respect to center of mass is r omega square j cap. Or you can also write it as v square by r j cap. Rishi, is this clear?
Yes, sir.
Okay. What if it had angular acceleration as well? Suppose alpha was non-zero. Okay. If alpha is non-zero, then the rate of rotation will be changing. Omega will be changing. And basically, if omega changes, v is equal to r omega, the speed of circular motion has to change. And for speed to change, there must be tangential acceleration. So if alpha is non-zero, the particles will have tangential acceleration also with respect to center of mass. And rotation is clockwise. Assume alpha is also clockwise. If alpha is clockwise, what will happen? That point of contact P will have tangential acceleration this way. And what is the formula for tangential acceleration? R alpha. Okay, so it will have centripetal as well as tangential. You will have to consider both. The problem becomes too lengthy or too complicated, but you will have to consider. If alpha is 0, the tangential acceleration won't be there, but radial acceleration has to be there because it is rolling motion or rotation is happening. Radial acceleration will be there for every point except the center of mass. Okay. Fine. So today we proved that for pure rolling, okay, that means rolling without slipping or skidding, the condition is that Vc should be equal to r omega. And also the sense of omega should be appropriate. Okay. If Vc is to the right, omega should be clockwise. If Vc is to the left, omega should be anti-clockwise. That is also there. That is why I'm putting a star here. Okay. So at a particular instant, if an object is in pure rolling or not, can be determined by comparing V and R omega. But see, it's quite possible. For example, you take a car itself. Suppose the car is initially at rest. V is 0, omega is also 0. Then V is equal to R omega is satisfied. Okay. But you gently accelerate the car. Okay. Car, bicycle, bike, whatever it is. You accelerate gently, then you can gain speed without skidding. Means pure rolling is possible while accelerating as well. Okay. And same with retardation also, or while slowing down also. You can apply brakes gently and bring the vehicle to rest without skidding. Okay. So if an object, if an object or a system is accelerating without skidding or slowing down without skidding, that means, see, speeding up or slowing down, VC is changing. And for it to continue pure rolling, for it to not skid, R omega also should change accordingly. Okay. If VC increases, R omega should increase. If VC decreases, R omega should also decrease for it to not skid. Now, what changes VC? Acceleration of center of mass will change velocity of center of mass. What changes omega? R cannot change. Okay, we are considering rigid body, so radius won't change. What changes omega is angular acceleration alpha. Okay, so if VC increases, omega has to increase. If VC decreases, omega has to decrease to continue pure rolling. And to continue pure rolling, or to continue rolling without slipping, continue means even when the vehicle is accelerated or brakes are being applied. To continue pure rolling, the rate of change of VC must be equal to the rate of change of R omega. That's all. How much ever the left hand side changes, if the right hand side also changes the same amount, they'll again be equal. And that is how the system can continue pure rolling. Now, rate of change of velocity of center of mass is nothing but acceleration of center of mass. Okay. I'll have to put a star here. I'll explain this later. Basically, it's the acceleration of center of mass parallel to the surface of motion, surface on which the object is moving. I mean, we can discuss deeper about this. It is possible that center of mass is not moving on a straight line. If the surface is flat, center of mass moves on a straight line. But if the surface is curved, center of mass moves in a curved path, then center of mass will have tangential acceleration as well as radial acceleration. Okay. So this AC, why I'm putting a star here, AC is the rate of change of speed of center of mass. So basically this is the acceleration of center of mass parallel to the surface of contact. Okay. This must be equal to rate of change of R omega. R is constant anyway, and rate of change of omega is what you call alpha. So AC should be equal to R alpha. This is the condition to continue pure rolling. Fine. At a particular instant, whether it is in pure rolling or not, you can check by comparing VCM and R omega. If they are equal, it is in pure rolling at that moment. If ACM is equal to R alpha, it will continue pure rolling later also. Like the example that we took here, we took AC 0, alpha 0. If AC and alpha are both zeros, then this condition is satisfied. Then it will continue pure rolling. Obviously, it will continue pure rolling because AC is 0, so VCM won't change. Alpha is 0, omega won't change. So VCM will always be equal to R omega. Once if it is equal, it will always be equal. None of them are changing. So it will continue pure rolling without accelerating. But while accelerating, if you want to check whether it executes pure rolling or not, you will have to compare acceleration. Okay, this AC is not centripetal acceleration. Don't confuse it. I better write it as ACM. Okay. Acceleration of center of mass should be equal to R alpha, where alpha is the tangential acceleration. Now, how does center of mass get acceleration? It gets acceleration from the net force acting on a system. So F net makes the center of mass accelerate. And how does the system get angular acceleration? The net torque acting on it gives it the angular acceleration. Fine. So questions based on this. questions based on cases where forces act on an object in rolling. Okay. That is what we will discuss in the next class. How it continues pure rolling. We'll include friction also in the equations. We'll include multiple forces in the equations. Okay. But we'll discuss all that in the next class. So let's quickly go through what all we discussed today. Basically, rolling, which is a case of combined translation and rotation. You imagine an object translating as well as rotating on a surface. Okay. What is interesting or what is important is what the point of contact does. So consider the point of contact, write an expression for its velocity. Vc minus r omega I cap. I assumed omega to be clockwise, v to be in the rightward direction. Then I got this formula. Okay. Then we discussed different cases of rolling. And based on pure rolling, we solved some problems where we found energy, then speeds of different particles of the system. And last thing we talked about is accelerations of different particles of the system. Okay. And then the condition to continue pure rolling even while accelerating or if some forces are acting on it. Fine. We'll stop it here for now. We'll continue in the next class. Thank you all.
Thank you.